So today we should discuss about regression diagnostics or more generally about assumptions, whether they are fulfilled or not in our data. I will go also into the brief excursus at the beginning, and I will show you how you can automatically create dummy variables in JAMOVI. So, as the first step, once again, we will visit our data file. So it means data file about flats. We know that instead of automated creation of dummy variables, we applied variable size 2, size 3, and size 4. But instead of it, in JAMOVI environment, we can take original variable, which is called synthesis, and we can ask JAMOVI to create, I would say, only artificial variables. So it means they will not be present in my data matrix. For computation. So let's see how it works. So here we have a brief description. So if you go into linear regression dialog, and then there is a special option which is called reference levels. We will try once again to apply this tool for synthesized variable, let's see how it works. So once again, let's go into analysis, regression, linear regression, and we would define once again as dependent variable price of flat, and C size will be coverage independent, and synthesis, as it is defined here as nominal, but maybe that would be ordinal, but still it should be defined as a factor. So here it is, you can see that by default, so it means you even didn't ask for preparation of dummy variables, JAMOVI recognized that synthesize should be recoded into dummy variables, and all steps here automatically computed are computed for reference category, the first one. As you can see, comparison of the second one to the first one, third one to the first one, and fourth one to the first one. So that's automatic default option. So it means the first category will be reference category. If you would like to reverse this step or change this step, you can go down and you can ask here in the second option for reference levels. And here you can change the reference category to the second one, third one, or the fourth one. So you can take another option, but once again, the first category, so it means the smallest villages is maybe the best one for us here. And the last one comment is that JAMOVI can do even more, not only dummy variables. You can see that these are called as default, but you can also choose some special option of so-called simple coding. So it means that the sum of all categories should be 0, but that's a special discussion about contrasts that can be applied. One, I would say, very nice property of this dialog for reference levels or automated application of dummy variables is that you can see here the note that if you apply dummy variables, then the level of the intercept represent reference level. So it means average price per flat with average size and from synthesized category first one. So that's a quite nice property that you have here also, the command which helps you to interpret results. So that's automated creation of dummy variables in JAMOVI, sorry for that. So here we are, and now let's go briefly into assumptions. and check for these assumptions in a linear regression model, as we only discuss mainly about the assumption that we should have at least one cardinal dependent, one cardinal independent, the relationship should be linear. We try to find whether it is fulfilled or not, mostly by correlation coefficient or even dot plot. But there are many, many more assumptions for correct application of linear regression model, and we will go through these. We will learn how we can check these assumptions, or more generally, we call these processes as regression diagnostics. I would like to say, first of all, that different software packages uses different tools for this assumptions check. So that's why the presentation will be slightly wider. So it means we will not only discuss possibilities that are present in JAMOVI, but I will show you also some possibilities that can be applied, for example, in SPSS or in other packages. So here we are, and here we have possible problems that can arise in application of linear regression model. So the first one is, and we solved this puzzle, I would say already, that we can have points that are called influentials or outliers. Influentials simply means that if the point is present in my active data set, then it will influence results. Mostly it will influence the level of individual slopes. And we know that such influential in my data set is the flat, which is the flat number 155, which has very, very big size. 439 square meters, but the price is only slowly below 3 million Czech crowns. And if you would apply also the computation, including this flat, then, for example, the slope for C size will be much smaller. We can check this property very easily. So if I go into filters, so I can cancel this filtering. So if I once again close this dialog, so currently there is no filtering at all. And I guess that JAMOVI can recompute the results. So once again, here we are, 155 is included. And if I try to recompute results, so once again, let's take regression, linear regression, price and C size. So the coefficient should be much more than previously. Previously, it was approximately 14,000 per square meter, and currently it is below 10,000. So that's quite a huge difference. And we can see that this point is influential. So that's, I would say, common sense identification of influentials, but we will go into more details later. I would go only back and at once again filter that we would like to filter cases with size below 200 square meters. So apply this rule. So currently, I guess once again the flat 155 size is lower. I would say that's active. So I guess it's active currently, 155, yeah, and this flat is filtered out of the, our computation. And here you can see once again recomputed result. C size value of slope is slightly more than 4,000. So that's it. And that's brief introduction into influentials. We will also discuss other problems such as heteroskedasticity. So we will discuss about different levels of so-called residuals for different levels of independent variables. Then we will discuss about the problem which is closely related to time series data. So it means if you repeatedly observe the same phenomenon many times and individual observations can be somehow correlated if they are close in time. And we will discuss about, I would say, classical problem, especially in social science data, which is called multicollinearity. So it means about strong relationship between individual independent variables. But before we start, we need to go into brief excursus about so-called residuals. So first of all, I would go into our data matrix and into our computational analysis, linear regression. And if I ask for price and C-size model for simplicity, and I will go into save, I have at least some options in JAMOVI to save some new variables into my data matrix. And the first option, which is present here by save, is to save so-called predicted values. What does it mean? So if I would take individual level of C-size for individual flat, and I will take this C-size into the equation intercept plus C-size slope, so it means 4,289 multiplied by C-size, I will get regression estimate or predicted value of the price by my regression model. So it would be predicted value. So I will get a new one column here at the end of predicted values of prices of flats. And then at the end, I can compare real prices and predicted prices by my regression model. And this difference is called residual. So it will be our next option. So once again, if I would like to apply computation of these predicted values, so if I click here, I can go into regression matrix. And here we are, this is, for example, a real price for the first flat including the analysis, so 650,000. And predicted price here at the end is slightly bigger, approximately 35,000 more. So these are predicted and these are real prices. And once again, the difference between these two is residual. If I would like to compute these residuals, I could go into transform computation, or another option is to go once again into linear regression dialog, and I can here ask for residuals directly. And if I go once again into data matrix, there is new one column called residuals, and these are differences between predicted and observed values. So you can see that, for example, the first residual is approximately 35,000 as we computed very simply from this value and this value. So these are residuals, and I would call it maybe generally by layman language as that these are, I would say, mistakes made by regression model. So this is the difference between real value and value which is predicted by my regression model. And we would need these residuals for some regression diagnostics later. That's why we will briefly discuss about these. First of all, I would like to say that classical residuals, it means what is just computed in JAMOVI by save, or it would be the difference between real value, so that small y and small y is het is predicted value. So this is so-called unstandardized residuals. So it means they are following scale of the original variable. So it means, for example, here for flats, they are in check rounds. Here you have some properties of these residuals, or how we can compute some of the properties of these residuals. So we will not go into details of these equations, but we can only say that this matrix, which is called H, computed by this expression, is quite important for some diagnostics of residuals, and as it is called as H, it is sometimes called as Het matrix. So if you will go into details of regression diagnostics, into some regression textbook, you can find more about Het matrix. There is also, I would say, maybe slightly better version of these unstandardized residuals, and they are called as predicted residuals. The logic behind these predicted residuals is very close to classical unstandardized residuals, only the difference is following. The logic of predicted residuals, and unfortunately JAMOVI is not capable of this computation, is that if I would be computing residual for the first flat, so it means number 2 included into the analysis, I would take this case outside of my computation. So it means, for example, in JAMOVI, I would filter out this case and I would compute regression model for the rest of the data. And I would apply the result for this regression model for the rest of the data to this first case, and I would compute the predicted value and then residual. So it is predicted residual. That's why here in a lower index, there is a -I. So it means that for prediction, this case was omitted. So these are residuals which are in original scale. So it means here, for example, it would be in check rounds, but mostly for some advanced regression diagnostics, I need somehow to standardize residuals. And that's why we usually apply classical, the easiest standardized residuals. So it means I would take these unstandardized residuals and only divide these by their standard error. Here's the variance. So square root from this is standard deviation. So here you can see how it works. Or you can, if your software package apply predicted residuals, also apply standardization to these predicted residuals, and you would get so-called jackknife residuals. They are maybe even slightly better, but it depends on the software package which of these residuals can be computed. Unfortunately, JAMOVI can save only classical residuals, so it means unstandardized. In JESP, there is no such option. Even in SPSS, you can save all of these, so it means unstandardized as well as standardized and jackknife residuals. So capabilities in SPSS in this context are slightly broader. And we will discuss once again about residuals in a few minutes in the discussion about heteroskedasticity. Fortunately, for heteroskedasticity, it is enough to have unstandardized or predicted residuals. So also in JAMOVI, we can work with this. So once again, we would go into influentials. And we know that influentials are the points in my data that will influence the level of the slope. So it means if I will include or exclude the case, it will have big impact on the slope of my computation. Once again, the difference was quite huge one. So instead of 14,300, there were approximately only 9,000 here. So it's very big difference. General, and I would say most common procedures for diagnostics of these influential points, if I'm not including discussion about plots. Once again, it is much better to see the plots before we start the computation. But the most common computation tool for diagnosis of influentials are called DFBetas. So these DFBetas are based on very simple logic. I would take real value of my slope if the case is included. So for example, if I would include the biggest flat, 9,000 would be this original slope, and I would take slope if this point is excluded. So 9,000 minus 14,000 would be DFBeta for this big flat. And I'm able to compute these DFBetas for all flats. So it means I will apply regression in number of times, which is the same as number of cases. And every time I will exclude the point from the computation and will subtract the real slope and slope with omitted case. So it is quite a computational intensive procedure, but once again, software packages can do it for us. And for every case, and also for every predictor, if I apply multiple regression, I will get DFBeta. Once again, unfortunately, JAMOVI and JASP cannot apply this DFBeta logic. We will show brief introduction of this DFBetas in SPSS environment. And for possibility to somehow evaluate these DFBetas, we must somehow standardize these values, and we call this as NDFBetas. Here is formal equation, which is behind the scene, and very simple rule in the literature for finding influentials is saying that if you take the computation of standardized DFBetas, once again called as NDFBetas, then you should compare it with the level 2 divided by square root of a number of units in your data. So once again, if my data file currently 2 excluded is based on 261 cases, so I would take 2 divided by square root of 261, and this would be cutoff level. And standardized DFBetas that will be higher will detect influentials in my data. And there is also an alternative to DFBetas, as number of DFBetas is related to number of predictors, and also for interceptor constant there is a special DFBeta, so that's why there is quite a lot of these values. So instead of DFBeta, sometimes we are computing so-called DFFit. DFFit is very simple. Once again, I would be computing predicted value of the flat if I apply regression to all data, and then I will omit, for example, the first case, and once again compute predicted value. And the difference of these fitted values, that's why it's called DFFit, difference of fit, I will get DFFit for this first case. For the second case, once again, applying regression, with and without this case, etc., etc. So 261 times regression computed with and without, and I would get DFFits. Once again, SPSS is capable of these computations, JASP and JAMOVI are not, and once again, it is better to standardize this DFFit. It is called NDFFit usually, and recommended cutoff level is 2 divided by square root number of units, small n, divided by number of parameters. So it means number of individual slopes and intercept, so these are parameters. So that's about options that are not available in JAMOVI or JASP, but JAMOVI and JASP uses, and I would say it's also quite common, diagnostics for influentials, which is called Cook's distance. And there are many recommendations in the literature, but I would say that the most general, and also you can find this in Field's textbook, is that if Cook distance is bigger than 1, then maybe the point could be influential, and maybe, once again, if it is influential, it should be omitted from my data analysis. In JAMOVI, you can find these Cook distances on 2 places in a regression dialog. You can ask for saving Cook's distance directly in your data by save option. So we know about it. So once again, if I go back, and here I can click into Cook's distance. So I would get in data matrix a new one variable, which is Cook's distance. And if I would like to find whether some case is extremely high or not, or at least one case, I can simply, for example, ask for analysis, exploration, descriptives. And here we are. I would take the variable Cook's distance, and I can see very simply that minimum is nearly 0 and maximum is 0.3 or slightly lower. So if recommendation Cook distance by 1 means influential, there is no influential currently. Once again, the reason is that maybe the biggest influential, the flat with 155 case number is currently omitted from the analysis. Maybe it would be nice to see if I will include this point into the analysis, what will be Cook's distance for this point and whether I can detect this point by Cook's distance as influential. So once again, I would go into filters and I would make this filter non-active. So currently we should include all data into a computation. You can see that JAMOVI is recomputing the results, and currently you can see very big difference. Minimum is still very low level for Cook's distance, but the biggest value is 28.2. So if I go down once again by data matrix, I guess that for flat number 155, I will find this extremely high value of Cook's distance. So it means that this point is influential. And once again, recommendation is omit this point from my regression computations. So that's how it works. And you can also instead of these computations and checking Cook's distances in data, so you can also find a special dialog, which is directly in assumption checks. So the first time we will go into assumption checks, and here you can ask for Cook's distance table. And here you will find automated summary of Cook's distance. So it is even not necessary to ask for saving Cook's distance into your data matrix, but you can only ask for this data summary, and you can find that at least some value is extreme, and maybe some points are possible influentials and should be omitted from computation. So that's about influentials. We know about consequences. Influentials usually change slopes, and the easiest tool is to omit influentials from the computation. Let's go to the second problem, which can be present and is quite often present in social science data, and it is called heteroskedasticity. Maybe before we start, I would go back and I will exclude one again this extreme flat from our computation. So I will once again make the filter active. So JAMOVI directly recompute our results. And once again, this flat is omitted from the computation. And maybe before we start, I would go once again to this regression dialog, and I will start with residuals plot as the first step for the computation or detection of heteroskedasticity, as it will be maybe easier to explain what is it through the picture. So here we have some pictures that are usually a classical set of residual plots in different software packages. So you can find similar charts in SPSS environment as well as JASP and JAMOVI. And here we can see some plots that can be useful, but I will use this last one. Here we have our predictor. So it means centered size of the flat and residuals. And classical assumption of linear regression model and assumption which is behind the usage of ordinary least square is saying that if you are increasing the level of the predictor, these residuals, so it means once again difference between predicted and real values, should be all the same along the scale of independent variable. But here you can see slightly different pattern. The residuals are even bigger or smaller if you go from the lowest C size to the biggest C size. So residuals are somehow related to C size. At least it seems to me that the shape of these residuals is like this shape, which can be described here on the chart. So it means that for C size, our data are so-called heteroskedastic. So the variance of residuals is here increasing by C size level. So once again, we call this as heteroskedasticity. If we would go into opposite case, so homogeneity of variance of residuals is opposite case. So in this case, according to C size level, residuals would be only something like in this shape. So it would be the case of homogeneous variance of residuals. We should discuss briefly about the impact of this heteroskedasticity for the computation. So if your data are heteroskedastic, and it seems that they are in our case, at least from this chart, then you will get big standard errors of individual coefficients or slopes. So it means that if you are evaluating individual slopes by t-test, it can happen that this variable is artificially biased, so it is bigger than it is really is, and then the ratio of estimate and standard error could give quite small t-value and quite big p-value. So in extreme, the consequence of heteroskedasticity is that t-test would be statistically insignificant, and it would inform you, okay, I would exclude this variable from data analysis. So this is how it works. What is possible consequence? Fortunately, in our case, even it seems there is heteroskedasticity, there is no such big impact, as t is still very big one and p-value is also low one, but still we should briefly discuss about possibility how we can detect heteroskedasticity. There are many statistical tests that are implemented in different software packages. Unfortunately, in JAMOVI or SPSS, there is no such test implemented, but we can very simply show how very common Glejser test can be applied in JAMOVI environment, and for CHESP and SPSS, it will be very closely option for application. So here we are. So we need for Glejser's test, and that's Glejser's proposal, to take absolute values of residuals as dependent variable, and then we will create regression model for the same set of independence. Only symbols alphas and alpha j are applied here to differentiate from betas as coefficients for original regression. So it means for prices. Currently, we will be trying to prepare a model for absolute values of difference. Once again, residual is the difference between real prices and predicted prices. If we would like to apply this Glejser's test in JAMOVI, it's quite easy. So we would save residuals as the first step. Fortunately, we have these in our data matrix from previous computation. So here we have, and here we have residuals. In the next step, we would need compute the new column, which will be absolute values of these residuals. And then we will apply a regression model to these absolute values of these residuals. And before we start, we would need only, I would say, interpretation tool for Glejser's test. So if we apply this regression to absolute values of residuals, so if there is effect of predictor on absolute values of residuals, then heteroskedasticity is present in my data. So it means that I will be evaluating mostly p-values for these individual slopes. And if p-value will be low, it means there is proven heteroskedasticity in my data. Last one comment from theoretical point of view, if there is heteroskedasticity and I know that the influence is very big one, so it means my t-tests are statistically insignificant, I should apply weighted least square techniques. We will not discuss about this option, but if you would like to know more, once again, you can consult the literature. Unfortunately, JAMOVI is not capable of weighted least square technique. In SPSS, it is possible also to apply weighting directly in linear regression dialog. So there is one more window here for weighting variable in SPSS environment. But once again, we would like to apply computation of Glejser's test, so we would follow previously described steps. So first of all, we will compute absolute values of residuals. So here we have residuals, and here we would compute absolute values for these residuals. So we can go into data, we will click into new one column. Here it is for computation, and here we can click into compute dialog, and we can compute new one variable. So I would call this variable as absolute values of residuals. And the function would be that I would take absolute value. I hope it would work as ABS and then brackets. And then I would need to type residuals, which is the variable present in my data. So I hope it works. So ABS is maybe by big letters, I guess. Let's start. Yeah, now it works. So ABS functions are in big letters. And here I can check whether it works. Minus 35,000 plus. So all here values should be the same as here in the column of residuals, only with pluses. So it seems it works. So this is how we can compute absolute values of residuals. And the next step would be apply regression to this absolute values of residuals as dependent variable. So it would be, I would say, artificial dependent variable. Here we are in our regression dialog. We would need to take price and do not include into dependent variable, but instead of it, we would take absolute values of residuals. And as the first model was including only C size, so it would be our covariance. So here we are. And if we would like to evaluate heteroskedasticity, so we would go into C-size row for model coefficients, and we can see that T-value is quite big one, P-value is statistically significant if we use classical phrase. So it means there is effect of predictor on absolute values of residuals, and heteroskedasticity is present in my data. Once again, fortunately, it is not maybe a too big problem for my computation, but sometimes it can be. And once again, if it is the case, I would need weighted least square techniques, and unfortunately, I would need to go out of JAMOVI as JAMOVI cannot apply this computation. I will only briefly skip into the last slide of the presentation, as very, very similar problem, at least by its consequences and also by its solution, is called autocorrelation. Once again, mostly I can find autocorrelation in data that are time series data. So it means, once again, I would repeatedly observe the same phenomenon many times, and I will find that residuals for different time points, especially if they are close in time, would be very similar. So in statistical discussion, I would say that these residuals are correlated, and we call this phenomenon as autocorrelation. Assumption for application of classical linear regression model, and especially ordinary least square, is saying that these residuals shouldn't be correlated at all, so they should be independent for individual observations. And if I would like to check it, so maybe the easiest would be to choose similar tool as for heteroskedasticity. So chart for residuals versus time. So if I would have time series, I would go into classical plots as here, and here I would put time by residuals. And I would see whether there is some pattern. These patterns could be like this curve or something like this. So then residuals are somehow correlated. So it means if previous value is quite close to the next one, then there is autocorrelation. Of course, this, I would say, subjective evaluation of autocorrelation is maybe not the best one, but you can also apply some tests. Before we start to go into details, I would like to say that consequence is very, very similar to heteroskedasticity. So once again, big standard errors of coefficients, t-test statistically insignificant, or also confidence interval would be quite wide. Once again, solution is weighted least square techniques. And if I would like to detect autocorrelation, that's very easy to show, but unfortunately, we do not have time series data here. So it would be only, I would say, artificial example. You can apply Durbin-Watson test. So if I would go back into our computation, and I would go here into assumption checks. So here is by default autocorrelation test. And if you ask for this computation, I guess that we will get a new one output. So here it is. So here is Durbin-Watson test. Once again, our data are not time series, so that's only artificial case. So I would get here the value of the autocorrelation. Durbin-Watson statistics, it can be in the range from 0 to 4, and here p-value. If p-value will be statistically significant, then autocorrelation is present in my data, and I should apply once again weighted least square. Once again, for this case, we do not need autocorrelation test as our data are not time series. So that's only how it works in JAMOVI environment, and the same style can be found in JASPER and in SPSS. Last one, problem that can be found in linear regression model applications in social science data, and I would say this is very common problem, is called multicollinearity. So if I try to apply ordinary least squares, I expect ideally that my independent variables are totally not related to each other. So full independence for independent variables would be a strong assumption, and also some relationships to dependent variable. Of course, that's ideal case, and in real data, we are not usually following ideal cases, but still, if the correlation between independence is not big one, that's not big problem. But if this relationship is very strong one, then it can happen that final solution cannot be found, so it means cannot be computed. And if the relationship is not so strong, so it means still can be computed, it can still have consequence. Once again, standard errors could be inflated. So this is quite similar to heteroskedasticity or autocorrelation case. It means t-test can be insignificant. And also, and maybe it is even bigger problem for multicollinearity, estimates are not stable. So it means if I compute regression and include some more independent variables, maybe that the effect of original variable can be totally reversed through, from example, from positive to negative values. And that's the big problem. And now let's discuss how we can detect a multicollinearity. Maybe the easiest, and I would say maybe this is not the best one, possibility is to compute correlation coefficient for independent variables. So if I go back into my computation, so I can click into correlation matrix, and I can, for example, try to find whether size is somehow related to balcony, and I can see that this relationship is quite big one, 0.17 or 176. The recommendation is very simple. If this per correlation coefficient is about 0.8, maybe there is strong multicollinearity, and maybe you should try to solve it, and we will discuss about solutions on next slides. There are other options, and these options are mostly based on so-called tolerances and VIFs. The tolerance is very simple. You would take one independent variable artificially as dependent, and the rest of independence you would take as independent, and you would compute regression. And you would compute R squared. So it means, once again, the level of explained variance. And you would take 1 minus R squared for this regression. And tolerance is a value which is saying how much are related these values, or 1 minus how much they are related. Recommendation for the level of the tolerance for multicollinearity is that if it is below 0.2, or sometimes even 0.1 for some liberal statisticians, then there is multicollinearity. So that's recommendation for tolerance. For VIFs, which are only just inverse 1 divided the tolerance, recommendation is just opposite. So above 5 or above 10. So these are recommendations for VIFs and multicollinearity case. In some packages, unfortunately not in JAMOVI and JASP, there is also some characteristic which is discussed as condition index, and this is square root of the maximum and minimum eigenvalue. And the computation and recommendation is that above 30, there is multicollinearity, but again, it is not present here in JAMOVI. So let's see how to detect multicollinearity by tolerance and width practically in JASP and JAMOVI environment. So once again, I would go into linear regression model. So for simplicity, I would once again define price. I would take C size and Balcon as first covariates. We know that relationship for these two was quite low, and I would go into assumption checks. And here we have collinearity diagnostics. And if you ask for this collinearity diagnostics, you will get a new one table called assumption checks, including 2 columns, VIFs and tolerances. Once again, we know that these two can be recomputed from each other as it is only inverse value. And once again, recommendation for tolerance is below 0.2 or 0.1, then there is multicollinearity. VIFs tolerances are nearly 1 here, so there is no problem at all. Or just opposite by VIFs above 5 or above 10, it is approximately 1, so it is not above 5 or 10. So there is no doubt that there is some multicollinearity currently present in my data. I'm not sure if I will include some independent which would be binary, if it would work also for this assumption check. So let's try. Yeah, also you can add nominal or binary variable, and VIFs and tolerances will be computed here in JAMOVI, so everything is okay. And if there is multicollinearity, there are some possible solutions. First one, and maybe not the best one, that's why there is a smiling icon here, is to ignore the problem, but it can happen that it will have big impact on my computation. The easiest solution is to leave out one variable which is closely related to another one. Theoretical recommendation from statisticians is maybe that if you will get more data, multicollinearity will disappear, but once again, it's quite impractical. You can use factor analysis as the first step. We will discuss about factor analysis later in this course, so you can replace originally related variables by factors that will be totally unrelated. And the most complicated step for solution of multicollinearity, unfortunately, it's not present in JAMOVI and JASP. You can apply syntax for H regression, which is installed in SPSS by default, which is called ridge regression. The trick which is applied in ridge regression is that instead of classical computation of estimates, which is based on this equation, omitting this part and this part included, you will add some small constant multiplied by unit matrix, and you will somehow slightly shift your estimates, but you will avoid multicollinearity. So that's so-called rich regression. Once again, consult for more details in the literature. So that's all for today about basics of regression diagnostics. Once again, we know currently about influentials, heteroskedasticity, autocorrelation, and multiculinarity that can be present in real application of linear regression dialogue.